All right, people. So today we're going to be talking about the kinetic molecular theory of gases. All right, so we're just going to read them and we're just going to talk about these four things, okay? There will be a little bit of some equations that I talk about, like how they came up with postulate number four. I'm going to skim through it. The book does this crazy long explanation, like this one right here. Ugh, ew, on it, but we're gonna ignore that. All right. Well, no, we're not. We're gonna talk about it later. All right. Um, so let's start off with one. The particles are so small compared with the distance between them that the volume of the individual particles can be assumed to be negligible. So this one right here. Um, the purpose of the kinetic molecular theory of gases is to explain the gas laws. It's to support it. It's to say the reason the gas laws work is because of these four things. Some of these are assumptions. Some of these assumptions fall apart under different conditions. And we'll talk about that. But let's check it out. Um, if you can't really get a visual of this, the particles are so small compared to the distance between them that the volume of the individual particles appears to be zero. So if you have gases, and gases have a lot of space in between them, so let's say you have a gas particle here, and then the nearest gas particle is over here. Well, this is a lot of space in between those particles. And if the space in between them is way bigger, it's way bigger compared to its size, you can say that the gas is a tiny little dot that doesn't take up any space. And that allows us to do a lot of these calculations. Some of these calculations fall apart under very high pressure, or very low volume, or very high heat, because, or very cold heat, right? The extremes tend to make things not work, and we'll explain why. All right, but if you can't really get that visual, here is kind of like how you would see a liquid, and then a gas would just have way more space in between them. Okay, so that's what postulate one is saying. Postulate two: the particles are in constant motion, and the collisions of the particles with the walls of the container cause pressure to be exerted. And so if you have a little, oh, I'll show you. So take a look at, I think I've showed you this before. If you take a look at the pressure, right? So if you add more particles in there, let's say we add particles, well, every time they crash into the wall, that's what creates pressure. If you increase the number of particles, you increase the collisions on the walls, and when you increase the collisions on the walls, you increase pressure. If you make the walls bigger, pressure goes down. If you increase the collisions of the particles by a lot, well, the particles will produce a lot of pressure because now they are crashing into it a lot. They're going to crash into it a lot, and they're flying three dimensions. It's not just two dimensions. They're flying in the x-axis, the y-axis, and the z-axis. They're flying three dimensions all over the place in straight lines, not crashing into not losing energy when they crash into each other. And then not attracting each other. That brings us to postulate number three. The particles are assumed to exert no forces on each other. They are assumed to neither attract nor repel from each other. What does this postulate do? Well, what it's saying is that the gas particles, when they crash into each other, when they just come in and crash, they don't lose energy. They just keep going. They'll bounce off, but they don't lose energy. In reality, that's not true. They will lose energy. In reality, the particles might carry some electrical charge. They might carry some attractive forces that we're going to talk about later. They're going to have some attractive force that will move the gas from its path. If it moves the gas from its path, it loses its energy and it loses the pressure it makes. That makes calculations very difficult. So the ideal gas law is a simplification of nature. It's a simplification of what happens to gases. If we assume that they attract or repel each other, we are changing the pressure by that, because now they don't crash with the same amount of energy. Well, now they won't cause the same amount of pressure. Same thing with temperature. The temperature of collisions is related to the energy in the particle. If the particle loses energy, well, it's going to lower in temperature. So it's going to complicate things there. The first postulate one affects volume. Pretend that's pointing at the V. There we go. So some of these are there. Some of these postulates are there so that we can use the equation. All right, we make these assumptions, we make these statements, even though we know they're not 100% true. They are 100% true when the equation works, and that equation works a lot. All right. Or it helps explain certain things. Okay. Now, the final postulate says that the kinetic energy of a gas is directly proportional. So the kinetic energy of a gas is directly proportional to your temperature. So R times T. And in this case, I believe it's a different value of R. The value of R, the value of R, where's the value of R? It's 8.314. I thought I had it somewhere around here. Sorry. But it's 2/3 RT. Now, where does this equation come from? This equation comes from physics. Actually, in physics, you do have to memorize this equation, unfortunately. But what this equation says, it's based off of this postulate that the kinetic energy and the temperature are related. If temperature goes up, kinetic energy goes up. This 2/3 R, it's just a number. It's just a constant. So that times temperature will give you your amount of energy. Where does this come from? It comes from this thing that I showed earlier, but I'll simplify it. This complicated equation up here on the top comes from physics. It comes from this thing, that kinetic energy is equal to 1/2 mv squared. M is in kilograms, and then V is meters per second. And since it's squared, the units of kinetic energy become kilograms times m squared over s squared. But instead of writing all of these units, we call that a joule. You have to know that. Write that down somewhere. Tattoo it across the knuckles. kg, m squared, s squared. Got to represent. So we have our joules, right? That the joules is a measure of energy. And so it tells us that temperature is a measure of energy. Temperature basically measures how fast particles move. It's an average of how many particles move. If you have a thermometer, right? You have a little thermometer. The number of collisions that occur on that thermometer, the faster or the more energy that the particles crash with, the higher the temperature, the hotter it gets. All right, so now what this equation has done is it kind of laid this foundation that, well, when particles move, they cause pressure. Well, when particles move, they have kinetic energy. The more kinetic energy they have, the more they crash. The more they crash, well, the higher the temperature. So it kind of paints a very nice picture. Now, in physics, it's not just kinetic energy. There's like momentum. There's like all these different variables. This little 3. So the 2 comes from this equation. The 3 comes from the x, the y, and the z direction in which things move. We're not going to go over it. I highly encourage you to skip that part of the text. But the part you shouldn't skip is this equation, and to know that the kinetic energy is in joules. One more thing, this value of R is 8.314 joules over moles times K. I have a feeling I'm forgetting a unit. I always forget the units on this one, to be honest. I had a little brain fart, but I don't want to waste time, so I'm going to reference it really, really fast. It's joules per K. Come on, you're wasting your time. You're wasting your precious time. 8.314. Yeah, I was correct. 8.314. So this is for that R. So it's another gas constant. And it's just another gas constant. It's another gas constant. Now, what am I talking about? I think that's all I have to talk about in this section. In the text, it explains how the kinetic molecular theory supports all of the different gas laws, right? So the kinetic molecular theory helps explain the relationship between pressure and temperature, which is Gay-Lussac's law. All right. The kinetic molecular theory also helps explain how volume is related to temperature, Charles's law. So now you have a mathematical model that explains it, and you have a conceptual model that supports it. That makes it a very, very strong argument and a very solid way of explaining gas behaviors and predicting gas behaviors. So basically, developing a very solid understanding of how gases behave and how they should behave. This one right here, it helps explain the relationship between volume and moles. So Avogadro's. So this is a very, very good theory. Now, in the text, there's a small section right here that says this was extracted from experiment and this was extracted from theory. When it talks about theory, it's referring to like Newton's laws or like physics problems, the 1/2 mv squared, and then talking about momentum. And then this one came from just performing experiments on gases, but the equations are basically the same. The only thing the theory missed out on is the gas constant, because the gas constant shows up in experiments. But what we're going to do next is we're going to talk about something called real gases. Now, real gases do take up space. Real gases do have attractions to each other. And what other things did we have? I always forget. They do exert forces on each other. Some of them aren't in constant motion. Sometimes they can be locked in place. Sometimes they get stuck in place. So a lot of these aren't necessarily true, but they are true in certain conditions. They are true in certain conditions, and that's where we study it, and that's where we apply it to, okay? So don't ever see the word theory and be like, oh, that's just a theory. It's not based off of anything. No, it is based on looking at experimental data and explaining it. That's what it does. It explains someone else's mathematical like laws. All right, but that's about it, people. Make sure you read over this. Make sure you understand that the volume has to be negligible, and they don't exert forces. These two assumptions are very, very important, but they're also wrong, and we'll talk about how they affect this equation and create the real gas law. Hasta luego, muchachos and muchachas and everyone.